Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Start. Okay, so anyway, it's a great pleasure to introduce Professor Woody Srissaran, who is from the University of Nebraska in Lincoln in the Department of Computer Science and Engineering. Woody got his PhD from the Illinois Institute of Technology in 2002 and has been working on issues related to memory management and, as we're going to see today, more broadly, issues around scheduling and performance in the runtime system. So with that, I'll give...
Well, thank you very much. So what I'm going to talk about today is what we call the context-aware scheduling framework, which is something that we have built about for the past 16, 18 months. It's a collaboration between the Java virtual machine and the underlying operating system. This work is actually in collaboration with my student Fung Zhen, who is actually working here at Microsoft somewhere, and then Hong Jing, who's my colleague at Nebraska. So let me start off by talking about the trend that we have, and we've been seeing this since around 2001, that managed languages, such as Java, and we have seen ASP.NET and such, are making inroads to large servers. And we're talking about eBay, we're talking about application server, JBoss, all those things. And they are actually very important. It's a very important market sector for Java, for example, because this is one that brings in quite a bit of money, as well as being used pervasively in the marketplace. Now, in this kind of environment, one of the things that happen is that the application tend to be extremely memory intensive. It would allocate tons and tons of objects, and then it will use gigabytes of heaps. And they're also highly concurrent. A study of Java application server benchmark find that it can spawn 500, 600, 700 threads concurrently while it runs. So this is one of the trends that is happening that we are seeing commonly today. Now, in addition to the change that we see in this adoption of the managed code, we also see more change happening almost pretty much everywhere, right? If we look at it from the hardware standpoint, we see that the processor is a little bit wider now. It's not 32-bit anymore. We see many cores per die, right? When we start looking at the OS, we now see OS with 50 million lines of code. We start seeing OS that has backup feature, as well as security feature, as well as all kinds of features that you can dream of, and it's all in the OS now. In terms of application, we just have more and more and more and more layers, right? We have the VM, we have the app, we have the library, we have all kinds of runtime system, we have the application server, then we have the application running on top of it. So this is the way that we are moving. And one of the things that come out from this is that some of the behavior that we see in application today are slightly different than what we would have seen in the past. For example, if we look at the application layer, we have runtime system running, as well as applications that are running. And runtime systems sometimes actually compete for resource with the application it's actually running, right? For example, you can look at just-in-time compiler, which create object in the heap or the code cache. You can look at garbage collection that basically steals some cycle away from the application as it tries to do its work. From the hardware standpoint, what we see is that the performance gain is harder to achieve by just sitting back and waiting for Moore's law to take place and cranking up the speed. We now have to be creative. We have to write application that can be good at parallelized code. We have to do some work here. So some of these things that we used to take for granted in terms of like every 18 months, our performance is going to double. Well, it's no longer true. Now, what about the OS, right? And that is this thing that I was looking at. Even though we add a lot of features, some of the fundamental feature hasn't really changed for decades, right? For example, I was in at our university, we are changing the way we do qualifying exam this year. So I have to come up with a reading list for the people. And one of the reading lists is the textbook that we're going to choose for the OS. So when I asked around all my system people and said, what book should we use? I said, does it matter? Anything from Silvershot version 1 to version 7 would work, right? Because basically, the scheduling will still be there, the semaphore will still be there, the process management will be there, producer, consumer, all those things will still be in there. So basically, it hasn't changed a whole lot. Now, considering like in version 1, they might compare Multics to something else. Now they compare Linux to Windows Vista. But the fundamental core scheduling, memory management hasn't really changed a whole lot. So this is one of the things that I want to point out, that perhaps we may want to rethink about the way we design OS slightly to meet up with some of the changes that we are seeing at the application level and at the hardware level. So change in hardware, changes in application development processes, changes in runtime behavior, more concurrency, more advanced runtime system, may have take place, but then one of the things that we have seen is that some of the research, especially in academia, may have lagged behind the common practice. A good example would be garbage collection. From 2001 up to this point, 2001, 2005, we've seen a lot of garbage collection paper going out to PLDI, OOPSLA, but yet none of them have actually looked at the garbage collection in the server domain. All of them were done using toy benchmark, spec JVM98, spec JVB 2000. How would that apply to something like JBoss, WebSphere, right? It's unclear how those things would apply to large server environment. And the OS itself is somewhat antiquated. It's built for fairness and responsiveness, but is that enough to deal with some of the changes that are happening right now? So that's the main premise behind my talk today, is that let's take a look that if we were to change the rule of the game, if we were to be able to modify the OS and provide some info so that it adapts slightly to some of the things that we need to run the application well, what would happen? So in the back of our mind, we kind of know that somewhere in there when we write concurrent program, there is this scheduler that lurking in the background that can cause all kind of havoc with our concurrent code. This is a well-known problem to the point that they actually came up with a name for this, right? The first one is called unfavorable scheduling. You could go back to the paper in the late 80s. You can find in a lot of parallel programming papers, they refer to this term as when the scheduler show up unexpectedly and start messing up with the concurrent program that you have. It could stop something in the middle of a critical section, because the critical section is safe, then it can go suspended and cause all kind of backlogging. Recently, we have a paper that is going into OOPSLA, and one of the word that this used to be my favorite word, but now I have a new favorite one. The reviewer mentioned this word. They refer to unlucky scheduling. And the key word here is luck, right? When we're talking about gambling, good luck is good. Bad luck is not good. When we're talking about computing, when we have luck involved, it may not be a good thing, right? So when we go back and look at the word luck, and it's a success or failure apparently brought by chance rather by through one's own action. And unlucky scheduling is mainly based on chance, right? It's the chances a scheduler may schedule something that will work or won't work. So in effect, a lot of things that a lot of researchers as well as people who who write concurrent program tend to think of scheduling decision as a fact of life. That it is something that will happen, it's something that we cannot avoid, we just have to find a way to deal with it, right? It's just like raining, it's just like those kind of things. It's a fact of life. So let's rethink that a little bit. So what I'm going to do today is I'm going to try to achieve two goals in this talk. The first one is I want to take a look at how scheduling, or unfavorable scheduling, or unlucky scheduling, impact negatively the garbage collection performance. Okay? And what we're talking about here is not the obvious one, like, well, I'm doing garbage collection and a scheduler comes in and suspend my thread. If that's the only thread to do garbage collection, I got nothing done. That's not what we're going to talk about here. We're going to look at something that is more subtle, right? Something that may not be as obvious, and a lot of time it would escape us as one of the problems. And the second one we're going to look at is we want to see if we can change the scheduling policy in such a way that it can improve the garbage collection performance once we identify the problem. So that's one of my first goals. The second goal is we want to investigate the impact of unfavorable scheduling on concurrent program. And we want to modify the scheduling policy to increase parallelism. And specifically, we want to see how unfavorable scheduling can cause backlogs such as convoying and contention, and how can we modify scheduler to get rid of some of those. Okay? So that's pretty much the basic goals I want to talk about. So let's talk about the infrastructure a bit. To do this, require a little bit of modification. Most kernel today don't communicate that well with the JVM, and JVM do not communicate that well with the kernel. Besides some basic system call that it need to get memory to do those kind of things. So we built something called the VM guided scheduling framework. And the goal here is to make better scheduling decisions via collaboration between OS and VM. And the rationale here is that by having a virtual machine, most of the desired information that we would need to make this work can be easily obtained from the VM. VM is a single point of execution. It does provide you with an environment, so it has rich information that you can use. Normally, people use this inside the VM to do, optimizing compiler, to do all kinds of things. But now we want to take this information and pass it along to the kernel and see if we can use the information in a more productive way. So this is how it all started. Let's assume that we have a Java virtual machine here. Let me just try one of these. There we go. And then we have the kernel down here. I think we trim off a little bit on the bottom. So right now, this is the way things kind of work. We have Java thread. It may have some sort of thread multiplexing, but eventually it's going to be mapped to native thread so that you can take advantage of the multi-core processor, right? So that the native scheduler would be able to send out your thread to multiple core. Now, what we want to do today is build this framework, right? And this framework, even though we only list 2, we can have more, and we are working on more to add on to this. So the first 2 that we're looking at here is the allocation monitor. And if you ask me why do we look at allocation behavior, I will tell you in a minute why is that important. And then we want to look at the log usage monitor, which means that we modify the allocator as well as the monitor enter, monitor exit kind of function to get the information that we need. Then we pass that information on through the communication channel, which is something that we connect between the VM and the kernel. And we use system call to wake up the kernel so that it will go fetch the information. And then from that point on, the scheduler will take the information from the communication channel and then apply the corresponding context-aware scheduling policy so that at the end, what we're going to do is we're going to start mapping thread to the CPU in a particular order. That will be beneficial to some of the runtime systems. And again, what we want to do here is we want to improve the runtime system performance without causing the side effect like deadlock and starvation. So we'll get to that in a minute. So the monitoring service is there to represent a good balance between accuracy and overhead. Okay. So if we have a choice between very highly accurate data, high overhead, versus reasonably accurate data, low overhead, we'll take the reasonably accurate one with the low overhead. Again, this is done dynamically. We cannot spend too much time doing all this, otherwise the performance hit's going to be severe. And then we're going to do most of the analysis in the VM. And the reason for that is because we don't want to push this down to the kernel. We want to get information and process information in the VM so that we pass just the necessary information to the kernel to save some time, as well as not stealing cycle away from the kernel when it has to do some other kind of work. And the communication is done through shared memory as well as system calls. The policy that we set up are basically, they have to meet this two generic property. First of all, it doesn't guarantee that the policy we set up will work all the time. And if that does not work, you have to be able to fall back to the default policy. So the way we build the policy is always on top of the default Linux kernel policy. And then if we have an open system where we have native as well as managed code running side by side, our policy does not apply to the native code. So then the native code would just use the standard normal policy. This is only applied to the specific application that we need to apply the policy to. We have escape mechanism to avoid starvation and live lock. One of the things that you can imagine is that we probably want to extend the quantum time. That's one of the things that we want to do with the scheduler. How much can we extend? If we extend and this particular thread is a rogue thread that just keep renewing this, we can have live lock, we can have deadlock, we can have all kinds of issues, starvation. So we want to limit how many times that this thread can renew its quantum. And for the time being, we set it to 5 because that seems to work well for us, but we can set it to any number we like. It can be configured. And then we have the system is capable of having customized configuration for every application through metadata structure. So we have this metadata repository, and if you launch two Java applications, two instances of VM, they can actually have different policy that governing the way that they're going to be scheduled. Okay.
So you're putting this in the context of a virtual machine, but I guess my question is, how reasonable would it be to use it in a regular native environment, just like a regular runtime?
So that's a good question. I think it can be done. The problem with the regular runtime is that, for example, if we were to monitor the lock usage, right? Some people use the pthread library to do the semaphore, locking with the thread. That's great. You can modify there and you can get the info. But what if some people use their own version or use something else, right? Now all the library has to be gathered up and it has to be modified so that the information can be passed on. So it's a little bit more complicated because there are more sources of information that have to get through the kernel. But other than that, it can be done. That's the only challenge that we find. Some people, they don't want to use a standard library. They link their own. Then that library has to be modified in order for it to work. So how can we trust that? With the VM, it's a little bit easier because we now have a central point of execution. So let's look at the first one. And this is part of this work was appear in ISMM 07. But the one that appeared in ISMM 07 was a simulation result, and now we have implemented it. So the result I'm presenting here is slightly different than the one in ISMM. So this is the key insight about why do we need to monitor allocation behavior. So what we have here is that, when you look at a single-threaded program, Java program, and people have hinted at this for years, right? That there are this kind of phasal relationship that they have. That you would allocate object to a certain, at a certain point, and then eventually, once you allocate enough, you start using them, so you won't allocate as much anymore. And then eventually, those objects get used, they die off, and then you allocate it some more. Paul Wilson have pointed this out in his opportunistic garbage collection. He called that the compute-intensive phase and allocation-intensive phase. I think Trish Shushlimby has pointed out something like this in one of his papers in 05 at PLDI. There's a lot of people. Shending has also noticed something like this. So people have hinted at this for years. So we look at this a little bit more. So we went in and we download 20 apps, server as well as non-server. We tried them all out. We found that this phase do exist in all applications. And the more important thing is that when you see this drop, which means that that's when the allocation, the object are being used and they start to die off. On the y-axis here basically indicate the life size, which means the amount of live object in the heap. And when you see a drop, that means those objects no longer reachable. What we see is that there is a correlation between this drop and the allocation process. That if you map out the allocation as some sort of a time function, at a certain point you will see that there won't be a lot of allocation at all. Sometimes zero, sometimes very few, and that's tend to map very well with the time that object dies. And we find this in all 20 applications that we try, server and non-server. In the server, we look at each thread. We don't look at them as a collective. Otherwise, you miss this point. Then, in all 20 benchmark, more than 85% of the parsers actually map to this drop. Okay, some of them are parsers do some other thing. Sometimes it has this iterative searching, walking down the array, it would parse. But it doesn't have anything to do with this. But most of the parsers actually map to this drop. So we take that insight, and this insight was presented last year at OOPSLA 07, and we basically just take a look at this and use this information to detect these phases, right? So we have allocation phase, which basically mean that there are a lot of objects created, but not too many die. And then we have compute-oriented phase, which basically means there's not a lot of object allocated, but there's a lot of object that die. All right. So we look at this, and then what we came up with the term is we call it a heap working set. Is that when you have an allocation followed by the computation-oriented phase, this represents a heap working set. What it means here is that you allocate enough, and you have time to use those objects, so some object will die off. That is considered to be a heap working set for us. You have a question, Dave?
So you're showing it in with time measured in allocation size.
Right.
And I wonder if you have any intuition on if time were measured in cycles, what the curves would look like.
We'll get to that. It's going to be in quantum. When we get to that, it will be slightly in quantum. Okay, but we'll get to it in a little bit. So we got this part, right? So everybody clear about the working set? So that's what we have so far. This is the part that you just asked, but it's not going to be about cycle, but it's going to be about quantum, which basically represents some sort of time. In time sharing scheduler, each allocation phase can take multiple scheduling quanta to complete. A lot of time we see 2, 3, 4, 5. Sometimes we see 22, not very often. Most of the time it's somewhere between 2 and 5, right? So it means that you go in, you allocate a little bit, your thread gets suspended. Then you come back and allocate some more, your thread suspended. By the third time you allocate enough, and you have enough time to use them all up. So the allocation phase is now be broken into pieces, based on the scheduling. And this is the unfavorable scheduling we're talking about so far. So when you have this thread being suspended in the middle of allocation phases, right, it doesn't have heap working set in the heap. It has what we call partial working set. Right? It's only a small portion of the heap, the allocation that's already in the heap. So when the GC is called, and if you have a lot of these, what you end up seeing is that you have a lot of partial working set in the heap, but yet when you come collect, most of those objects cannot be collected because they have yet to get used up, right? And this is one of the key insight that we found is that when we have multi-threaded application, they leave a lot of this partial working set in the heap. So as you come in and do the garbage collection, you will not be able to collect as efficiently, especially with generational collection, where you have a small nursery and a much larger full collection, mature collection space.
So what are your assumptions about when GC is triggered?
So when GC is triggered is when the heap is full, right?
Okay.
But this one is what we're going to look at here is mainly when GC is called, and we're implying here a minor collection. Okay, let's say we use generational collection. So when a minor collection comes in, right, heap is mainly occupied by partial working set. Because each time a quanta comes in, you only allocate a portion of the allocation phase. But if you start, let's say you have 100 thread. You start right here, you go to the next, another small portion. It will take a while for you to get the whole allocation phase complete for one thread. And most of the time, you don't have a lot of allocation phase completed in the young generation. And since young generation tend to be small, it will fill up with all this partial working set, and you cannot get efficient minor collection going. Okay? So let me give you a little bit more illustration. I simplify this problem slightly. Well, quite a bit actually. Let's assume that the allocation phase is divided into 4 units of allocation for these 3 threads. So you have the green, the pink, and the blue, right? And the computation-oriented phase is in the gray, which means that you allocate this much and you give it a little bit of time to use up the object so that they would die. If the current scheduler is used, something like a round robin, and since they tend to break up the allocation phase into pieces, what you end up seeing is that you will have the heap that has a little bit of the pink, a little bit of the blue, a little bit of the green, but yet not full green, not full pink, not full blue in there. So when you do garbage collection, right here, when you try to do the 9th unit, which means that the heap is now full and it would fail, garbage collection get called, you have 3 partial working set in the heap, right? And this partial working set will prevent the minor collection from being successful in collecting the object. And this is the interplay between scheduling and threading and garbage collection that actually give you some insight of why it would actually not being successful. One of the reasons why we came up with this idea was that, as we were hammering out on this server, we noticed that as we add more thread to the program and we increase the heap accordingly, we find that the minor collection tend to be less effective as more thread are being added to the system, and we couldn't figure out why, because the heap has already been adjusted. We add the heap size. Then we start looking at this and we realize, it's a partial working set that just keep increasing, so that's why our minor collection are not as effective. So what do we want to do here, right? The idea is quite simple. we want to schedule threads in such a way that minimize the number of partial working sets in the heap. That's what we want to do with the scheduler. So to do this, we need the information from the allocation. We need to know the phase. And once we know the phase, then we would allow the thread to allocate, give it enough time so that it can actually have the whole working set in the heap before it actually being swapped out. Yes, sir?
What you just said about as you scale up the number of threads and you scale up the heap size, that the minor collections are becoming less effective. Why doesn't just scaling up the size of the nursery solve that problem?
It would. It would. But typically in hotspot, the way it works is that the nursery is set at the beginning. So let's say you start off with 128 meg, and this is what we use. And maybe Dave, you can confirm since you were one of the guys that built this. So it has 128 meg, and you set the nursery to be 1/10. So it has 12 meg or 13 meg, right? As you enlarge the heap, and hotspot doesn't automatically readjust. So basically, it will keep that ratio throughout. So the scaling up would maintain the same ratio as it goes along. Now, you can go in and modify this, right? You can enlarge the ratio so that as you increase the heap, you would also try to increase the ratio between the nursery and the mature so that the nursery now looks bigger. It takes a bigger portion of the heap than the mature. That can be done. We didn't try it that way, just for the fact that most people who are using it out there would not adjust this, and they don't have a mechanism to dynamically adjust this after they launch the program. The heap will get adjusted, but the ratio won't.
So it's not enough that the nursery stays 1/10 of the heap size. You actually have to increase the ratio, not just the absolute
Right.
size.
That's right. And we tried that, and that works very well. We modify hotspots so that we can do that. It's for the other work, but we tried it, and that works quite well. But most people won't have that option. So what we do here, we just make the scheduler do the work for you, which may not be the easiest way, but at least it's a way that people don't have to mess with their code, but they have to mess with the scheduler. So I don't know which one is better. But anyway, this is academia, so we can try all kinds of things, right? Yes?
So also it seems like, anytime you have this kind of tuning parameter, right, where you say, well, is it 1/10 or 2, you run into the problem that, it'll change and people will just get it wrong. I mean, so
Yep.
I don't know if this will solve that problem, but it seems
Right, and it will change in dynamic, right? One of the things that I like about the Appel collector is that it does adjust this slightly, right? As you keep going, the Appel collector nursery size is not fixed. But most commercial VM use fixed size nursery for the reason that you can tune it. If you know the workload, you can tune the nursery size so that within that workload it works very well. But once you fall off that cliff or went beyond that workload, it's not sure how it's going to perform, right? Most of the time it doesn't perform very well at all. But so we're messing around with those little things a little bit as we playing with this. All right, so that's the goal here. So basic idea now would be something like this, right? You will let it allocate the whole working set, give it enough time so that it can get used, then you swap it out. Then you allocate another working set. Give it some time for it to get used, you swap it out. And this, by the time you try to do the third working set, you would find that most of the heap is now empty. And if you were to do minor collection, you'll be successful. So that's a very simple idea that we try to do here. All right. So we introduced this thing called memory quantum round robin. Round robin typically is based on time. You give it 200 milliseconds, that's your round robin cycle. This time we use memory quantum. And the reason for this is because applications are memory intensive. And they have this phase relationship that is based on memory, so we want to end up using memory quantum as a way to predict when should we swap out the thread. This is built on top of a traditional time quantum round robin. So, so that's how we would go about doing this. So one of the reasons why we end up using memory quantum is we found that time is not a very good measurement of memory. You can have a thread that allocates 10 kilobytes, it will take only 20 milliseconds to do it. And then you have another thread that can allocate the same amount of memory using half the time. So time alone is not good enough as a way to do this. So we came up with this memory quantum round robin. We assign each thread a memory quantum instead of a time quantum. Memory quantum size is dynamically adjusted during the runtime. So we can shrink and grow the quantum for each particular thread. So it's a little bit more customized. And we use that information to adjust the priority. Linux has this ability to adjust priority up and down by 5 points. If you are here, you can go up 5, you can go down 5. We're going to use this information to do the priority bumping as well. Typically with Linux, the way that they bump priority is based on CPU usage. If you have an I/O bound thread, the priority goes up. which means that it get more time on the priority because on the processor because it doesn't use as much. And if you use a lot of processor, your priority goes down. So that's how this kind of works, and we're going to use the same mechanism, except that we use a different criteria to do the adjustment. The adjustment is the same mechanism. And we implement this in Linux and Sun Hotspot VM. So let me talk a little bit about the shrinking part, right? So we know about this phase, and we modify the allocator to detect the phase, right? The phase mean that we're going for a certain period of time, and we have very little allocation. So what we do here is, let's say it start off, and this system is not like a profiling system. So it start off clean. It doesn't have a profile run. It start off with just the default with the same quantum size for each priority. You start off with a quantum unit of X, or whatever U, right? And you go there for a whole unit, and when the time unit come, you notice that you have no phase. It means it needs more quantum. It will ask for another renew. So now it has 2 quantum. It basically about to get preempted, but it won't. It will stay there, and it will ask for the next quantum. It will continue to run. By the time we get to the end of the second quantum, if we still see no phase, it will then go on and ask for the third quantum, and we limit this quantum to 5. Because most of the time that we see in our, in all our application, you never need more than 5. You rarely need more than 5 quantum to really get through a phase. So we set it to 5. This, in effect, avoids starvation. Because if you don't set a limit, if there's a rogue thread that just keep allocating, you can go on forever, and then no other thread will get to run. So we go with this. We get to the 3, and if some time between in the second and third quantum, we found a phase, then this thread will now be assigned 3 quantum. And it will just remember that. So next time comes in, it will go 3 quantum. Periodically, we may want to recheck this because program phase do change and the quantum size do change. So it might go too long for a while, right? Eventually, periodically, we will come in and recheck this thing again and test for quantum. And if next time we find the quantum to be within the 2 unit, we would then reduce the quantum to just 2. So that's how it kind of grow and shrink. Now, we have to tune this periodic, how often do we do this? There's a lot of tuning involved here, and we'll get to that in a minute. The priority is based on a very simple notion that if you have thread that you have a small working set, it is likely that if it goes in, it will be able to complete its task very quickly. And if you have a thread that has very long quantum, there's a chance that you might not even finish that, right? Which means that it will leave more residue in the heap that cannot be collected. So we try to bump up the priority of a thread that has smaller quantum, and this is only +5, -5. So it's certainly within the requirement of Linux. We just use a different criteria to bump up and down the priority. And then, so we use the one with the shorter priority, and we use that number to then calculate the priority boost or priority drop. In terms of evaluation, we went to use a few benchmarks here. For the capo, we went in and take out all the multi-threaded version. The single-threaded version won't help us here because this is not about, it's about multi-threaded program. So we pick out the 4 that are multi-threaded, and these are the thread number that are listed on the back. We went on and pick out the SpecJBB 2005, which is superseding the SpecJBB 2000. And then we went on and run JBoss, and we put SpecJApp Server 2004, which is a standard benchmark for application server from Spec, which spawned 407 threads. And then ECPerf is the one that Sun released back in 2000. It eventually becomes SpecJApp Server 2001, and it spawned 405 threads concurrently. We tried them all out. We run a generational mark compact collector. We set the heap size to be the maximum life size times 3. So it gives you a reasonable size with reasonable GC overhead. And the methodology is we run everything 5 times, the default one as well as our modified version, and we take the best run of the 5 and we compare the 2. The difference between the runs is about 10%. Actually, between the 5, there's some differences, but they're not that far, especially with application server. This thing runs for hours. So all the variants that you see actually got kind of factor out over time. Whereas something like the capo and a small benchmark tend to have more variance, but all of these run for a lot longer than the single-threaded benchmark, just for the fact that it's a little bit more heavy. So they have less variation than, let's say, if you run some application that only run for 10 seconds. Yes?
So you were talking about detecting a phase, and it seems to me like are you going to talk about how you detect the phase in the future, or
No, actually, the basic idea is that we modify the allocator and we take a few information to detect the phase. For example, we use the method call as a way to guide of when do we actually want to monitor the phase. But typically what we do is, as the allocator get requests, right, it take a little bit of measurement of time using a sampling. And then when you have a sample rate, a sampling, and you look at the, sampling is based on interval. And when you have some interval that has very little, that's how you notice whether you have a phase or not. So that's basically how we measure this thing. So see how this thing works. So we look at the GC time reduction. And this is, again, is generational collection. And we talk about the traditional mark sweep and other thing later. So GC time reduction in percentage, we can see that in large server, these are the 3 large server that we're looking at here, we get about 20-some percentage in terms of garbage collection time reduction. This is one of the more successful ones. We get like 27%. Some of them we don't get a whole lot. Now, keep in mind that in this large server, we run them pretty heavy load. So garbage collection is quite significant. It takes a lot of percentage in terms of execution time. It's not like we set the heap to be so big that you rarely call GC. We call GC thousands and thousands of times in these applications.
So can you break out the fraction of time when you do GCs that you're spending in the first generation versus the full GC?
I have that graph somewhere else. I can show it at the end. Yes, we do. The factor is, I don't know. So the minor GC on average, well, the full GC is on average about 22 times longer than the minor GC in this system. Okay, and this is because there's a lot of heap that has to be go through. The heap size is said to be like 2 gigabyte, 4 gigabyte, depending on the application. So it's relatively large. And we set, I believe that we set the ratio to be like 1/4 nursery. 20% of the heap is nursery. Yeah?
Both generations are using parallel collectors?
For this one, we didn't. We will use it in the later one. And the reason why we didn't use parallel collector is that parallel collector does improve the throughput quite a bit, but it doesn't, I'll get to that slide actually it's the next one, isn't it? Okay, so this is the slide that I want to, if you use parallel collector, this goes up slightly. This doesn't really change, okay? You still have this big drop, which means that's one of the reasons why, when we have a fixed nursery, you can really tune this area very well. Once you given a workload that this is going to be the norm that you're going to be expected to see, you can really tune this plateau to basically almost like fix. It's going to give you this performance at this point. But once you get past that point, when the object lifespan becomes bigger and bigger, you start to see this kind of drop. Okay? So what we use here is just a standard collector. And so the red line is basically the standard round robin, and the green line is basically what we have with the MQRR. And this is for SpecG App Server 2004. Now, the other one is most of the apps are mainly giving out the execution time, except for this one that gives out the job per second. So application performance, what we see is that we have a reduction in overall execution time of about 1.4 to 15%. And the reduction in response time, this is only for server, is about 3 to 22% of how fast the response will be able to come back to the user.
So in terms of the response time, it seems like you might change the average response time and decrease it. But
the worst one might be longer?
Yeah, exactly.
Actually, it's kind of an interesting phenomenon. So even though there are 400 and some threads, right? Most of the threads are really worker threads. And there are like a few threads that have really this weird behavior that allocate a lot of objects, right? But they do quite a bit of work. Most of the time that we apply this technique, it actually works very well with this worker thread, right? Because they are the one that being spawned a lot, they are active most of the time. And you have this long one that allocate a bunch at the beginning, probably to initialize the program. And then it sit idling most of the time. Periodically would come in and do work. And those, since they're not active, they're not part of the play, right? They're not part of the scheduling. So yes, we actually see slightly longer delay time in the worst case scenario, but on average it's slightly better. So that may not be the best for real-time performance, because some thread may have to wait a little bit longer. But the idea here would be that if you give it more time, it can actually do more work. So the one that gets scheduled will actually be able to finish faster, but the one that have to wait longer may have to wait slightly longer in order for it to get to do the work. But once it gets to do the work, it can do it in one shot. So what we have, this is the other observation. It worked quite well with generational collector, right? And that is what we expect in a sense that because we have young, small generation, small young generations, so we have hard time fitting all the working sets in there. But as you move to like something like a non-generational collector, like a mark and sweep, you have huge space. You can fit a lot of working set in there, even though you don't get the whole allocation phase in. You can still get a lot of working set in there because you can wait its turn. It has plenty of room. The interval between collection is much longer. So that's one of the reasons that we don't see as much performance boost, or if at all, with the non-generational collector. And it does perform quite well in the tight heap situation. It does improve the time that the system would die, extend it out slightly, and then it has a better degradation toward the tail end of a heavy workload. So the summary of this first part is that the current time sharing based thread scheduler is not very GC friendly. We propose an MQRR, which is an allocation phase aware thread scheduling strategy that can reduce a GC reduction from 3 to about 26%. Yes?
So in benchmarks that have transactions whose latency you measure, it's possible that your heuristics for inferring memory quantums might infer multiple memory quantums per transaction. Or it might be that they always correspond to one.
I think for that, we've been thinking about this, and people have suggested this several times before too, is that, so we had this little idea before using this remote and local object, and we exploit this a key object opportunity, right, in our earlier paper. Basically, we look at this transaction-based web, like this, as there is an object that always allow you to determine the lifespan of the transaction. It's the one that pick up the connection, right? The one that pick up the connection will spawn a bunch more objects, and eventually, when everything's done, it just releases the connection. So we create something called the local and remote heaps, and we use this as a key object to predict the lifespan of the transaction, and we put an object that are transactional based into this heap where we can tune the size different than just a regular nursery. And that seems to work well, but it can go further, right? The further idea would be to use region-based and start dumping the transaction into a region. Make sure that you do calculation well, that object that escaped the region are moved somewhere else, and then you just don't collect. You just free the whole region. Take that away. You don't call GC at all, right? You just call GC to do the chunk thing. I don't know, I think Steve Blackburn has a paper at PLDI last year called IMIX or something like that. It's a region-based, but I haven't really looked closely to see how that would adapt to transactional-based. But then again, it's done in JAX RVM, so I'm not sure how well it will run this application server type either. So, all right. Second part of the talk, about 10 minutes. It's about effect of scheduling on concurrency. And this is somewhat of a hot topic with transactional memory going around everywhere, I think. There's a lot of people working on that. So we want to take a different approach to looking at this problem. Instead of trying to deal with this conflict, we try to avoid a conflict. Let's see if we can come up with a scheduling strategy that will allow conflict to be fewer, right? Or contention to be fewer. And that's going to appear in OOPSLA 2 weeks from now. So we know about locks, right? Locks are used as a mechanism to synchronize thread execution to prevent multiple threads from accessing shared resource. So we use lock quite a bit, right? In JVM, it used lock. It has thin lock, fat lock, and all that. In C language, we use semaphore to build locks. We use all kinds of mechanisms to do this to achieve these two goals. So when we use lock, we have this lock contention. Right? Lock contention means that somebody's holding a lock and somebody else wants to get to the lock, and it can't. It either can spin and wait until the lock becomes available, or it can get suspended and be back into the dugout, wait there until until it can come back and try to do it again. So we classify the type of lock into two different types in the multiprocessor system. You have inter-processor contention and intra-processor contention. So the inter-processor contention is a contention that can occur across multiple processors, and the intra is, of course, is within the same processor. So let me give you a very simple scenario here. Let's say we have two physical processors. We have thread 1 running on CPU 0 and thread 2 running on CPU 1. As we start looking, and this is a program counter, as it continues down, it gets to the lock. So the thread 1 is trying to access its critical section. It grabbed the lock, and thus the lock is now, locked together. It's in the critical section. It's continuing to execute. Now, thread 2 is trying to do this. This is done concurrently. Right? They're on two different processors. They're running the code that try to access the same critical section. So now thread 2 would not be able to access it because thread 1 is still holding the lock. So at this point, thread 2 must wait because it contends with thread 1. So it go into the dark hour, it's been waiting until the time is right for it to come back and try to get the lock. All right, so that's inter-processor contention. Intra, this can actually be intra and inter, right? But we're going to just give a scenario that we only have a single physical processor. We have multiple threads that are being multiplexed on this processor. So we have a thread 1 that actually is running and then hold the lock, run for a while. Because it's already have the hold of the lock, the data is safe. Nobody else can access the data while it's holding the lock. So now it's going to be preempted. Right? While it's being preempted, thread 2 comes along, want to access L02. But since thread 1 is still holding it, it can't. So it can spin and wait, or it can go to the dark hour and wait there, being block state, until thread 1 get a schedule again, run, release the lock, then thread 2 can come back and grab the hold of the lock. If you have a single processor, this scenario do exist. It can occur. We call this convoying, right? Which basically means that a thread is holding a lock and then it got suspended. And then another thread would come in, try to access it. Since it's still safe, it can try. It can get blocked. And eventually, once it get a hold of the lock, it can go on. So the waiting time here is the time that the thread must wait. Even though it has already been scheduled, it cannot execute. It must go back and wait until the time is right for it to be able to come back and obtain the lock. And typically, when this one releases the lock, it will send a signal to unblock the thread that's waiting on it. Right? So what kind of impact do we see? So we go in and modify VM, and we measure this waiting time, right? When we run SpecJav Server 2004, we run this on a 16-core machine, right? And the SpecJav Server spawned 407 threads. And what we see is that, of the whole execution time, there are about 30% of the time collectively that the thread actually spend waiting for the lock. Now you can imagine with 400 threads and they're trying to achieve some certain transaction, there must be some sort of sharing going on quite a bit within this kind of systems. And that's translates to about 30% of execution time, which is not surprising, right? Amdahl's always said the part that you can parallelize will dictate how much performance gain can you actually achieve with with more processor core. Yes.
When you say 30% of time waiting, do you mean actively spin waiting? Or?
No, it's actually blocking and things. Basically, it's trying. So what we did is, this is kind of unfair in a way because if it gets blocked, right? We will measure until the time that it actually can get to it. Because blocking is hard to control. Now, it has to wait, might be longer. Some of them has the first time is spin waiting. I think the hotspot it's not per se thin lock, but it's something similar, where you have the very flat lock and the inflated lock. The first time it's spin wait, right? Or first few times. After that, it actually gets blocked. But basically, this is the time that from the time that it tries to access and it cannot to the time that it can access, and we collectively sum up the time. So some of them occur in parallel, some of them occur serially, So it's about 30%. So how do we make scheduler contention aware, right? So the goal here is do not schedule contending threads concurrently on multiple processors. Easier said than done. How do we do this? We have 16 processors. We have thread waiting in the run queue. How do we, this guy is running and is holding a lock. How do we propagate the information across? We can't. People have tried this and they fail. It's just way too complicated. The delay is too much. It leaves the system in unstable state. It crashes the systems. So this we cannot do, but we'll try anyhow. And then the other one is do not preempt the thread holding a lock, and we want to prevent intra-processor contention. So the way we did this is something like this. So let's assume we have a Java virtual machine. We have 6 threads running. We have 3 processors. It's kind of a weird number, but let's assume we go with 3 for now. The one with the same color mean that they do share some kind of resource, right? So they share some locks. So this two share, this two share. This one independent, this one independent. Okay? What we do is we cluster them. Now, when we talk about cluster, if you have 16 threads, 16 processors, maybe clustering may not be a great idea because you're now not going to have full parallelism, right? If you have 16 threads, 16 processors, each of them can have its own processor. And we would deal with that in a little bit. But this one, we assume that we have 400 threads and 16 processors. Somehow, they have to serialize, right? They have to go into the queue anyhow. So we're going to try to find a way to be more intelligent about putting them into queues so that they actually have less chance of contending. So we're going to find a way to do clustering at runtime so that we can come up with this kind of mapping. And then we're going to transfer it down and start mapping this thread to actual processor, and we're going to perform load balancing. And then eventually we'll apply this critical section first, which means that we will not let thread get preempted in the middle critical section, and the one that in the critical section will get a higher priority to go so that it will clear the critical section. Okay? So that's the basic idea for this particular approach. So the thread clustering, we're going to segregate thread into cluster based on their log usage. There are three major phases. There's a sampling phase, synthesizing phase, and the clustering phase. Let's go to each of them one at a time. So the first thing that we do is we record synchronization event, and this is done through modifying the monitor functions, right? So let's say that thread 1 is accessing a synchronized object called O1. We basically create a linked list, and we said O1 is part of this list. When it went down and synchronized O2, we create another object on this list. So this is what we call synchronization event vector for T1. It has two objects in there so far. So we go on and we build this for all the threads we have in the system. And then we set this size to be some number. It can be 1024, 2048, whatever. For this illustration, we set it to 8. What does 8 mean? It means that when one of these SE vectors reach 8 entry, it will stop. And we will do some sort of processing to come up with what we call the contention vector. And this is basically just the count. For example, this first lot is for object 1. That means this is for object 1, object 1, object 1. And you list how many times this object 1 is being accessed by that particular thread. So in this case, object 1 is accessed 3 times by T1. We just do this, right? So we build this thing called the contention vector. And this is not the actual contention, because actual contention is dynamic. You cannot predict that. This is the possibility for contention, right? And then we go in and we calculate what we call the similarity function. We basically take a conv vector and we compare it to its neighbor and see how similar they are in terms of accessing objects pattern. And then we go on to the next, and we go through this whole process until we combine all the conv vector and compare them against the neighbor. Whatever can be assigned to cluster are removed from this pool. Until at the end you have nothing to compare against, then you're done, right? And at the end of all this thing, what we want to get is the clustering information, where we have cluster 1, we have this threads that belong to it. Cluster 2, we have this thread that belong to it. This is a rough and gruff kind of approach, but it's not the most accurate way to do it. But I will show you later on that it's somewhat accurate. It's accurate enough that we can get some good information out of this and some good profitability out of this.
So you look at all and just trying to do analysis of the code itself to try to figure out?
We haven't done that. We can try to do that. Now, I think with, I know that there's some recent model checker that will allow you to look at some of the sharing and things like that. I'm still a little bit old school. I haven't touched some of the newer model checker that claim to be doing very well with large multi-threaded program. Some of the older ones don't do so well. We have a model checker researcher in our department, and they're still having some difficult time dealing with program with a lot of threads somehow, with 400, 500, 600, 700 threads. So that's one of the issues. But we can look at, that would be something that we're working toward right now.
So it's interesting. When you say 400 threads, it strikes me that how many different kinds of threads are
not
there?
that many, 10, 15, 20.
Yeah.
But in the leaving of the 400, if you can come up with some equivalent state so that you can reduce the set down, that would be good, right? But if you're going to try to explore all the possible combinations that the 400 may interact, that might be tough. But you can try to maybe limit that to a transaction. If you have a transaction of type A, these are the threads that are going to be involved, then we may be able to do analysis on just a transaction type base. That could be something. I'm not really a program analysis person quite yet, so most of the time I do things is mainly in runtime. Yes?
So, did you get any insight in how many of the logs that are acquired are actually going to be contented logs?
Yeah, we do. It's in the paper. I don't have the table right here. If you don't mind, if you're interested about this, this is a bad way to say this, but I have the paper on my website. It's a pre-printed version. The table is there. I can try to look down here too, but it might take me a while to find it because it's in PDF. But it is there. There is there's a heavy contention logs. How many of them are there? Light contention logs. How many of them are there? So we look through all those things. So we try to provide analysis of such sort. Yes.
I assume you have some way of giving up smoothly if a program locked a large number of objects, a large binary tree or something like that. Okay.
Yes. We do have something similar to that. Okay. So we'll get to that in a minute too. That's a good point. So now we're going to try to do this migrating cluster, which basically means that once you have the cluster information, you somehow have to map this to physical processor. And how we're going to map this. So what we do is we segregate the cluster into two groups. What we call strong contention and weak contention. Strong contention means that you should not split them in any way, because they have this tight contention between the thread within the cluster. And the weak contention is the one that if you want to do load balancing, split them up. Who cares, right? You can split them up and try to fill them in so that you get good assignment for each processor that are somewhat even. And you assign cluster of strong contention group to processor and then perform load balancing with the weak contention. That's what we did. So this is a little bit weird diagram to go through, but I'm just going to give you this number for now and just say trust me for now. But eventually I will go in and tell you how we actually came up with some of these number. Let's assume we have 6 cluster. After we go through the first process, similarity function and all that, we have 6 cluster. This cluster has 10 thread. This one has 2. And then we calculate the contention intensity based on the number of contention that's going on based on the lock that are belonging to this cluster and how much they contend. We come up with some number, and here's the threshold. Anything above 0.29 will be in the strong contention. Anything that is below this will be in the weak contention group. So at the end we have this, this is even, so it actually has to be greater than, not equal to. So we have this 4 clusters that are part of the strong contention and this 2 that are part of weak contention. All right? Don't mind the 56 as a page number. Then what we do next is we take the P1, which has 10 thread, and we just map that. That's a strong contention. It has 10 thread. We're going to map that. Before we do the first mapping, we calculate what would be a good average number. And we try to stay close to that. That's based on the number of thread and the number of processor. Let's say initially we have something like 8. So we come back with that. 10 is close enough, so we're going to map the whole cluster to P1. And once it's done, it's done. We're not going to add any more thread to P1. Then we have P2 and P3. Once we take P1 now, we recalculate again what is a good average number for each processor. And this time it's become average 2, and we have 7. So what we're going to do next is we're going to go through the strong contention cluster, and we're going to start mapping them. So we map, this was from the strong contention. So we map C3 to P2, we map C5 to P3. And then we're going to go in and look at the weak contention, and we're going to start splitting them up so that we end up getting about 7 thread per processor. So this one has 5. We only need 4. So we take C2, we take 4 thread, and we put that underneath C3. So at this point, P2 would have 7 thread. We take 1 thread away from C2, put it into P3, and then we add C4 to it. At the end, we have 7 thread. So it's 10, 7, 7. All right? That's how we did the load balancing. And then the next thing we have is called the critical section first scheduling. This is when we have this lock that you're talking about. So we keep track of the depth of the lock, right? And the one that has a big depth, we assume that somehow we want to give that a high priority so that they can release the lock soon. Otherwise, everybody else going to be, cramming on and try to get into this data structure, but it can't because it's holding the lock. But we're not going to give it unlimited freedom. We set the renewable quantum to be 5. So let's say if you're holding lock, you hold a lock and you grab another lock, you grab another lock, the depth is 3. If you don't grab any lock, the depth is 0, right? So anything that is 0 means that it's not in the critical section. Anything that above 0 will be either 1, 2, 3, 4, whatever. And we find that some of them grab like 20-some locks. If you have this weird data structure that you built, So you can go that far, and you can give it more critical more quantum to go through. But as soon as you reach 5 and it still hasn't released all the lock, then we just have to give it up, and we're just going to move on. So we give it more time, but we're not going to give it unlimited time, right? So we adjust the priority based on that. The one that has a deep lock, we give it high priority for the fact that it's likely that it might be enough to release all the locks so that other thread can go in and do work. If that doesn't work, then of course we give it up and we just go on and schedule other thread. So that's how we adjust the bonus. Again, similar mechanism existing in Linux. We just use different criteria to adjust the priority. Evaluation, same benchmark. We have 16 core processor, 32 gigabyte of memory. We're running Linux Fedora Core 3 and Sun Hotspot JDK under the OpenEdge JDK project. The heap size, depending on the application, it ranges from 64 megabyte to 2 gigabyte. This table basically indicates, what are some of the effects. Like say, if you have the SE vector size, which is a synchronization event vector, is the one that we record on the synchronization event. The size of this determines how accurate you're going to be. If you have too little size, you're only going to have very small sample data to calculate clusters, so that may not be that accurate. But if you have too many of those, and then also smaller size means you're going to stop to do the clustering very often. If you have long one, you're not going to stop as frequently, but each time you stop might take longer to calculate all this number. The similarity threshold is what we use to calculate whether the contention vector are similar enough to be in the same cluster. And if we actually provide too little of this, that means everything can fall into the same cluster. If we have too much, then nothing falls into the same cluster. That means everybody has its own cluster. The contention intensity threshold is the one that we use for load balancing. Again, if we don't do it right, one of the things that can happen is that we're going to have a lot of either strong contention intensity group or weak one, which means we cannot split anymore. So that has something to do with this 3 factor. So we run this. We adjusting this parameter one at a time. We run all applications to find out what will be a sweet spot so that this will run across all applications. And what we found is that this is clear that if we set the SE vector size to 2048, it works for every application. And the overhead is relatively low. It's about 3.5%. And the accuracy of all this clustering compared to the manually cluster. So what we did is we manually built a cluster, right, based on the manual locking information. The student did that. It took him a long time, but he built this matrix that has a manual cluster, and he compared against that, and we get about 70 to 80% accuracy, using this matrix. So we can gain all this with about 3.5% overhead, and we use this parameter across all 7 or 8 applications. This is what we end up getting. So we built 2 versions of this. The first version is called CASE V1, contention aware scheduling. The version 1 has no critical section first scheduling. So basically, it tried to just remove the contention by serializing thread, but it doesn't promote or boost priority. The second one has the whole shebang. It has a priority boost as well as a contention reduction. And we can see that we can reduce the contention in SpecJF Server 2004 by about 45%. That's the number of contention that we can reduce. For ECPerf is about 39 maybe, and JBB 2000 is about 30. But then notice that we do not gain on some of these. These are the app that has very little contention, and when we apply our technique, we gain nothing. As a result, we actually lose performance because we spend about 4% overhead, but our technique will turn itself off after it failed the first time, but still we fail quite a bit. These are short-run applications. So when you invest one time and you already spend that much, it's going to sting you somehow. So this we actually lose here, we lose a little bit here, we lose a little bit there, but we gain quite handsomely with the other benchmark. We gain about 14.8 some percent with the SpecJF Server 2004, and that's in terms of overall throughput improvement. By having less contention, you can deliver more job, and that's a goal here. Scalability is nothing to write home about. The weird thing about this thing, let's start with this one, is JF Server 2004. We have 16 core, we have 407 threads, so they are contending like crazy already, right? You don't have enough core to run. So we don't really gain, by adding more core, we don't gain a lot of performance in the first place because the number of threads is just so much more. But notice that while not gaining there, we gain slightly here. We can see a little ramp up, not a whole lot, only 13% here, but still a ramp up by reducing contention. This one we don't gain a whole lot, but we didn't have a lot of contention in the first place. But the interesting part is this one right here. This is Spec JBB 2005. By the way, I'm not claiming that this is true for every app. It just happened that JBB 2005 have 16 active threads. And we have 16 CPU. So theoretically, each thread will have its own CPU to run most of the time. And notice that we can actually gain the same throughput by using only 12 processor. So actually, if you have a choice of, this is just not a rule of thumb or anything yet, but it's just something to think about. If you have a choice of reducing contention by clustering, but you end up not going to use all your CPU, versus you're just going to let it run and use all the CPU, you might end up gaining some by reducing the contention and not using all your CPUs. Because you basically can achieve the same number of throughput by having 4 fewer CPUs. All right? So I'm going to get to the summary now. And we have one more slide left after this. We implement the context-aware scheduler, which is an approach to reduce lock contention. It can improve performance by about 15%. And it has better scalability, not all the time, just slightly better scalability when compared to the Linux scheduler with no contention awareness. And in this talk, I basically present you with these 2 instances of what we call the VM guided thread scheduling framework. Okay, and basically we look at the allocation phase aware scheduler and contention aware scheduler. In terms of future work, those are some of the questions that we try to answer right now. Should we make scheduler cognizant of execution context at all? Is this 2 examples good enough to continue on, or should we just abandon the ship? Can the language actually, if you use program analysis, can the language drop hints to help with scheduling control? We are doing this right now. We actually have a program analysis person in our group actually trying to drop some hints about scheduling for the mission critical applications that has smaller number of Java threads, but yet it's mission critical. To make sure that if the model checker fails at verifying all the type states, for example, we would try to control this during runtime to make sure that the unverifiable states are not going to be executed. The scheduler will not execute threads that get into that state that we have yet to verify. What about making other kernel component context aware? Can we use a virtual memory manager to start fending off threads that maybe just start a transaction so that we can save the precious memory that we have under heavy demand for the transaction that almost finished? I mean, think about this, right? Paging itself is almost like a resource contention. You are trying to bring in the page that you're going to use, but if you use and you swap, and you swap out the thread, it's going to be swapped out under heavy demand. So you're going to spend a lot of time swapping things in and out. Can we prioritize this? Early eviction LRU, that's something that Yanis Samarakdakis have invented a while ago. Can that be adapted to use with this kind of approach? Don't know. And then what are the impact of our approach on the transactional memory? I mean, transactional memory in some implementation pay dearly when contention occur, right? When you have conflict. It doesn't pay when you have no conflict. But when you have conflict, you pay some price. What if we reduce the number of conflict? Would that actually improve the transactional memory performance? All right, that's pretty much all I got for today. Thank you so much for being here. And
So I had one question. So you had the 2 things. You had the kind of clustering approach, and then you also had the idea of elevating the priority based on the depth of the locks. Did you try doing the depth of the locks without the clustering?
my student did. He didn't gain quite a bit. He didn't gain a whole lot there. So I think that's why he ended up dropping it. So he only have 1. We should have reported it. It might be in his thesis. I have to go back and look. Okay. I remember seeing that somewhere there.
You need the clustering then to make it useful to actually
elevate the priority. That's right. That's right. Yes?
So on the elevating priority, when is the elevation done?
Oh, when is the elevation done? Basically, if we go to the Linux, do I have it here? Hang on. Let me launch this guy one more time. The Linux scheduler has this, let me look here if it's in here. All right, yeah, I blocked it out. I'm not going to hide anymore. It has this idea of active and non-active queue, right? This is to ensure fairness. That, so let's say you have this different priority. It ensures that in each turn of the running, every thread, no matter which priority is in, going to get to run. They're going to have to get run at a different time. So one of the things that we normally do is when we adjust the priority, when we put that into the other queue, right? So you have this active thread queue where you have this priority list and all the threads are running. Anything that's just been suspended will go into the non-active queue at the priority level that is supposed to be adjusted. That's the normal way that Linux does it. And we just use that mechanism. We just calculate the priority adjustment not based on the CPU usage. We just based on the criteria that we specify here. So let's say if this thread is suspended, when it goes to the next queue and we want to boost the priority, it might be attached to one of these queues instead. So that the next time it runs, it will have the high priority. And then when it needs to be preempt out, we may simply just say, renew my quantum. So instead of picking another thread to run in its place, it will just continue to run that thread. For 3 more times, 4 more times. Yes, we do it at scheduled. The boost typically, normally it stays for a while, but then the next time if you run this, right? So the priority adjustment is being calculated every time it's being preempted, right? Before you move it back to the next inactive queue, you have to know what is the next priority is going to be. So we calculate that, but is remember the last one, and then it's basically going to have effect on the next drop. Because you start higher, you can only drop 5 points. So if you were starting, you were right at 0, and you move up 5, the next time you're only going to come down to 0. You will not be below 0, right? So that's how we do it. And basically, it's the same as what Linux is doing. We just change the criteria.
So with the changes in the priorities and things, so certain threads that hold more locks will get boosted over others, right? So were there any changes in per thread throughput that you saw? Like, was there unfairness that was introduced?
We see some. On average, it's better, but just like what Ben asked earlier, some of them actually get worse throughput,
right.
Because they have to wait.
So you know what the delta was?
I don't remember. It's not that significant though. And again, this is basically back to the nature of this application. You have a bunch of threads that are doing a lot of things, right? And you have a bunch of threads that are not doing a whole lot. Even though we have 407 concurrent threads, not all of them are in play at the same time, right? Some of them are not active. And the non-active one, if you wait 3 to 4 to 5 quantum, the throughput that is coming back, because it's a web-based, it just have all kinds of delay that you have to deal with the database and the user. It's kind of get hidden inside those delay that you're waiting for certain things to happen. So the throughput itself, even though it's longer, is not that significant, just for the fact that it's a web-based kind of application. If it is running on a single machine and it has very little external connection, you might see more, right? But for this kind of app, it seems to work just fine. Because the delay we're looking at here, we're talking millisecond already, right? So, that we're waiting for some database and we run different machine. We have a database machine that is not on the same machine as a web server, because that's realistic. We don't want to put them in the same machine. The client machine is also different. So you have this network latency that you have to wait a little bit and search through the cache, database cache, and all that. So it does incur some overhead, but not a whole lot, just for that fact. All right. Thank you.